This is Mrs. O'Neill for AP Chemistry, Chapter 8, Section 4, Bond Polarity and Electronegativity. The objectives for this section are to define electronegativity as the ability of an atom in a compound to attract electrons to itself, and also to examine the sharing of electron pairs that can be unequal between those atoms with different electronegativities leading to a polar covalent bond. So again, I suggest to pause, fill in the blanks in your student packet, and then play to hear my words. So what is bond polarity? There's two kinds of polarity, nonpolar and polar. So nonpolar are when the electrons are shared very equally. So neither atom has an extra pool or an extra charge. Nonpolar means everything is shared very equally. Polar molecules, on the other hand, electrons are not shared equally. In other words, you have a slightly positive and a slightly negative end. It's not going to be totally positive and it's not going to be totally negative like an ionic compound, but it's going to be slightly positive, slightly negative because one atom or element has more electronegativity than the other. And the symbol is usually a small delta with a little positive or a little negative next to it. So nonpolar would be something like fluorine gas. Very nonpolar, you have two atoms of fluorine, and because they're both the same element, they have the same exact electronegativity, so neither one is going to be able to pool on that electron that they're sharing between them more than the other, so it's nonpolar. Then you have something like hydrofluoric acid that's polar because now you have a positive end and a negative end. Because fluorine is more electronegative, it's going to grab that electron more often from hydrogen, those electrons that are being shared between the two. And then of course you have something that's very, very polar or ionic, where there's a total transfer of electrons. So there's your three types of bonds. Electronegativity, again, is the ability of an atom to attract electrons to itself, again, when we're forming a bond. So it's different than electron affinity. Okay, electron affinity is when atoms just want to gain electrons, but not necessarily in a bond. And we want to remember ionization is the giving away of an electron. But electronegativity is when there's a bond. So we're talking in between two atoms. And again, there's the trend. We've seen and talked about electronegativity increasing as you go across the period and decreasing as you go down. So of course, the more difference in electronegativity, the more polar, or again, could be possibly ionic, the bond is. So here's your bond type. You go from 0 to intermediate to large, so your bond type would go from nonpolar to polar to ionic. So again, your covalent character decreases and your ionic character increases. So that should make sense. Your type of compound and how it's being formed. So again, the trend, I always like to look at a trend as a diagonal. So I always like to remember fluorine has the most electronegativity and francium has the least electronegativity. So that hopefully helps you remember the trend. How do we compare these compounds? Again, the elements that are farther apart are going to be more polar. So if we go back to this periodic table, if we were to take fluorine and francium and make a compound, that would be very, 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 very polar because they have the most difference in electronegativity. Of course, the elements that are closer together, they're going to be more nonpolar. So in other words, if I would have nitrogen and oxygen together, that's going to be more nonpolar because their electronegativities are going to be very similar to each other. Give this some thought, see if you can come up with an answer. Hopefully you remember that difference that I just spoke of. So a dipole moment just basically means a polar molecule, a molecule that has a positive and a negative end. So polar and dipole mean the same thing. Those are two words meaning the same thing. How is it drawn? Something like this. Hydrogen would have a partial positive, fluorine would have a partial negative because fluorine is more electronegativity, it would get the negative. It also can be drawn like this. Sometimes they just like to put the positive and then the arrow where it's more electronegative. So dipole moments, when we line up a dipole molecule in the presence of an electric field, what happens? Well, here we have a lot of HFs just floating around. They're just going to kind of move around. They're going to have their partial positive and negatives. But now let's put an electric field. What do you think is going to happen? Ah, look at that. They line up nicely. You have all of your positives lined up with your negative side and all of your negatives lined up with your positive side. So that should make sense. Again, the force of attraction. Again, give it some thought. Hopefully that makes sense. So which molecules have dipoles? In other words, which molecules are polar and which ones are nonpolar? Well, it's going to be based off of down here, the geometry. Polar molecules are not going to be symmetrical versus nonpolar are going to be very symmetrical because the pull on the atoms are going to be the same. Okay, so let's think about that. There are 2 polar molecules we're going to talk about and 3 nonpolar molecules, but these are not the only shapes you're going to have to learn. There'll be more to come when we get more in the nitty-gritty, chapter 9, the geometries. But this is just a preview. So if something is not symmetrical, that means it's polar, which means one atom has more pull or one area of the molecule has more pull than the other. So if we look at something that's bent, this is going to be very polar because, again, we want to remember there's electrons here, and the pull of attractions of these atoms compared to the pull of attractions of those lone pairs of electrons is going to be different. So it's going to be polar. So if we look at something like water, again, we have hydrogen and hydrogen making that water connected to the oxygen, but we want to remember that there are 2 lone pairs of electrons that make the pull of these electrons different than the pull of those hydrogen atoms. And this is called a tetrahedral electron pair or geometry. So it's tetrahedral because we have 4 electron domains around oxygen, 4 areas where there's a bond or electrons, but it's actually in a bent shape. And again, we'll talk more in detail when we get closer to chapter 9. Ozone, another ozone. Now this is called trigonal planar because it has 3 electron domains. Okay, it has 3 electron domains, but the molecular geometry is still bent. It only has this 1 lone pair, but this is going to be considered polar, again, because those oxygens are different pull than the lone pair of electrons. Trigonal pyramidal, again, polar because of the different pull of attraction when we have those electrons on the top, that lone pair of electrons, just like ammonia. So here we have ammonia, we have our 3 H's, we have tetrahedral electron domain because of the 4 areas, but we have what's called a trigonal pyramidal because it has 3 bonds and 1 lone pair. So the molecules that we need to know that are nonpolar at the moment mean that they are very symmetrical. If you look at something that's linear, it's very nonpolar because this side of the molecule and this side of the molecule has exactly the same pull on that central atom. So if we look at something like carbon dioxide, this oxygen has just as much pull on the carbon as this oxygen. So it's the same pull, and this would be considered linear. We have something trigonal planar, also nonpolar because we do not have that lone pair of electrons like we saw in the other molecule. So this one, again, we have 3 electron domains. It's called trigonal planar, but there's no lone pairs of electrons. So even though it's a single and a double bond, that doesn't matter. This oxygen and this oxygen and this oxygen, all 3 oxygens have the same pull on that central carbon atom. Here's something called boron hydride. Again, trigonal planar. We have 3 electron domains, and all 3 are have the same pull on that boron. Okay. How about a tetrahedral? Again, nonpolar because you have 4 atoms pulling on that central element, and so they all have the same pull. So if we look at a phosphate ion, again, you have 4 electron domains because it's so it's a tetrahedral. They are 4 bonds, so a single bond and a double bond means it's still a bond, okay? It means it's still an electron domain. So all 4 of those oxygen atoms are pulling on that phosphorus element, phosphorus atom in the middle, very, very equally. So it is nonpolar. If we look at something like the ammonium ion, same thing. We have a tetrahedral, 4 hydrogens pulling on the nitrogen very equally. We have methane. We've seen him before. Again, 4 bonds equally being pulled on that carbon atom. Now, how can we make this polar? Well, all you got to do is change 1 or 2 or 3 of those elements. Change that hydrogen to a chlorine and boom, now you got a polar molecule. And the reason you have a polar molecule is because now chlorine has a different electronegativity. Chlorine is going to have a pull on that carbon element differently than the 3 hydrogen atoms that are attached to it. Here are some properties of ionic versus covalent bonding. You can read over those. Some of this you've probably learned in Chem 1. See you in class.